Let us study the Gauss law for a cylindrically symmetrical situation. Here we have been shown an infinite line of charge with linear charge density lambda. Lambda is equal to charge per unit length. And we have drawn this Gaussian surface which is a cylinder around this particular line. Now our Gaussian surface is finite and has length L. So only this portion, the interior of the Gaussian surface, encloses some part of the charge present on the infinite line. So here, this is the region which has charge. So this charge is going to be equal to lambda times L, because lambda happens to be equal to dq by dl, or it happens to be equal to q divided by L. Therefore, the charge enclosed is going to be equal to lambda times L. This is clearly understood. So let us note down our observations. Lambda happens to be equal to charge per unit length, and therefore q enclosed in this particular Gaussian surface is going to be equal to lambda times L. Now, because of cylindrical symmetry, the electric field is radially outward. This is an infinite line of charge. So the electric field is radially outward and moves radially away from the infinite line, as we are indicating here by the arrows. And hence, for the curved surface of the cylinder, the field comes radially outwards and is perpendicular to the curved surface. But whereas if we look at the top plane surface and the bottom plane surface, then in that case the field is along the surface. And since the field is along the surface, we can say that the net electric flux from this plane surface is 0, because the field is parallel to the surface. This we have illustrated in this particular diagram as well. For the curved surface, the electric field is perpendicular to the surface, and hence the angle between the area vector and electric field vector is going to be 0. And for the planar surface, the electric field is radially outwards along the plane of the surface, and hence the angle between the area vector and the electric field vector is going to be 90 degree, and thus cos 90 will be 0, and thus the flux that is outputted from the planar surface will be effectively 0. So the only flux that will get outputted will be from the curved surface. So let us try to write down the expression for the electric flux. We know that electric flux phi E is going to be integration of E dot dA, and that is going to be equal to q enclosed divided by epsilon naught. So here we need to consider only the curved surface, and thus this will be integration of E dA cos 0 degrees, that equal to q enclosed upon epsilon naught. So here we can take E common outside. Cos 0 will identically be 1, and we'll be left with integration of dA is equal to q enclosed upon epsilon naught. So we are here considering only the curved surface, because we know that the flux from the plane surfaces is 0, and thus this will be equal to E into the curved surface area of the cylinder. What is the curved surface area of the cylinder? Well, we know that it is 2 pi r times L. And hereby we can now substitute the value of q enclosed, which is lambda L times epsilon naught. Therefore, we get a radially outward electric field in this cylindrical symmetric situation, and that after cancellation of L happens to be lambda upon 2 pi epsilon naught r, which is the result we know and are familiar with, and Gauss law helps us to derive this result in a very simple manner.